So we have now studied one more project. Okay, so we have done sentiment analysis, then we have also understood, so we completed sentiment analysis using LSTMs. And the next thing that we have learned about language translation, and this was done using an encoder decoder architecture. So these two projects we have completed, right? So this has been done. Now the third project that we will be discussing today, this is basically an image captioning project. So when I say image captioning, right, what does come to your mind? What comes to your mind? See, you have an image, right? Let's say you have an image and something is happening here. So if you describe the scene or event of whatever is happening in the image in the form of text, it becomes image captioning, right? So this is a very nice project. This is a very good combination of computer vision plus natural language processing. Now the reason why I am mentioning this is because since this is such an interesting project, right, so you could actually do this and then you can add it to your CV. Okay, so you can add it to your resume and this will look very good because it will show your skills in both computer vision as well as in natural language processing. So that is why this project is a very interesting one. It makes things very interesting. So what we are going to do is we are going to do image captioning. So this is the topic that we are going to discuss today. If you remember in sentiment analysis, what happens, we just used basic LSTMs. We used a many-to-one architecture to get the sentiments, right? Next we increased a bit of level of difficulty and then we did language translation. So in language translation, what did we use? We used a many-to-many encoder decoder architecture. So that was something. Now what we are going to do, now this is basically image captioning. In image captioning also, this is kind of an encoder decoder architecture. How exactly, we'll understand. Okay, so how does image captioning work? Let's talk about the architecture first, then we'll understand. So to understand, first of all you need to understand the whole thing. So you have an image first. So you have an image. So let's say there is an image of a girl in a pink dress running with a balloon, okay, or holding a balloon. So this is a little girl and she's in a pink dress and she is holding a red balloon. So this is an image you have. Okay, so now you can imagine how the image looks like. Now if that is an image, you can imagine how the girl is looking like, and this will be basically the caption of the image. Okay, so girl in a pink dress holding a red balloon. Now this is what, this is a description of the image that you are seeing. Or what is this? In other words, this can also be said as the caption of the image. Okay, so this is not exactly the Instagram caption that we are talking about. This basically is a description of the image. Okay, so this is basically your image captioning. So first you need to understand that this will be hence your input. So your input will basically be the image and your output basically, or your label is basically this sentence which describes the image, right? So this is basically your task. So your input image and your output is a sentence. So this is the task. So how are you going to solve this task? So the very first thing is, whenever you have an image related task, since my input is an image, so you have to start with a computer vision. So what will happen, we will use some CNN architecture, some baseline model, whatever we decide, so that is up to us, some baseline model to first extract the features of the image. So you can extract the features of an image using a CNN model, and once that features have been extracted, the next thing that you are going to do, once after you have that, you will pass it through. So this basically, now this becomes your encoded vector. Okay, so this becomes your encoded vector. So what happens is basically you have the features. Once these features are extracted, this becomes the encoded vector. Now this is very similar to how we were doing the encoder decoder architecture, right? So this part is, so only the encoder part changes. Inside there we don't have LSTMs anymore, we will be having CNN which extracts the features. Now these features become your encoded vector. Now this encoded vector will now pass through LSTMs. Okay, different LSTMs it will pass to one by one. So you have the encoded vector will become the first hidden state here, and what will be the input here? Input will be the caption. So here the input will be girl in pink dress. Let's say this is the only thing that is the value, and let us not say that it has, let's suppose our only caption is girl in a pink dress. Okay, this is our only caption. Let us just reduce the caption size. Okay, and it will have two other things. So you will have the encoded vector, it will have one more here which will be a start token, and then there will be an end token. So this basically becomes kind of your encoder decoder architecture, right? But the difference is, instead of having an encoder, you will be having an encoded vector here that comes from the CNN instead of using basic LSTMs here. Okay, so this is very similar to your language translation. Okay, but the difference is, there you had LSTMs for the encoder part, here you will have a CNN architecture for the encoder part. So now your encoder is there, you got the values, it will pass like this. So start girl in pink dress and end. So this will be how your training will happen. Okay, so this will be the first image, you will extract the features, then it will take input as the tokens, and these tokens will be passed and these will act as the input. Okay, the next part, some other image will be there, so that will be passed, and then the tokens will be passed as well. So that is basically how your LSTMs get trained. Now here is the thing, so you have these girl in pink dress and stuff, start and end, and all these tokens. In the testing part, what will happen now? So in the testing part, you won't put all these inputs. So in the testing part, things will change. So your entire part of this will be, by the way, in training, entire thing will be, once given start, it has to predict girl, then it will give girl as input, it has to predict in, and so on. Okay, you get the thing. So this is the same thing. If you remember, we have talked about encoded target data, encoder, decoder target data, decoder input data, and everything. So that is the same thing here. Okay, in testing, now what will happen? So you will be getting the encoded value, that means you will be getting the encoded vector, that is the CNN features. You will extract using a CNN model that you will pass as your hidden state here, hidden state 0, and at the same time you will pass a start token. So this start token will first predict girl. Now the output from this girl will now pass here to the next RNN. So here girl passes, and this will predict in. Now this in passes here, this will predict pink, this pink passes here, this will predict dress. Now the dress passes here, this will predict end. Okay, so these are the tokens that will be predicted one by one. This is how your training and testing will be done. This is very similar to an encoder decoder architecture, just with a minority changes. Okay, so very little changes, but you can understand the architecture remains kind of the same. So what we are going to do is, we are going to now look into the code of how this encoder decoder architecture is actually working, right? So let us look into the code first. So here what we are doing is, I am not going to run the code. Now the reason why I am not running the code is because some of the code steps take a lot of time. Okay, so I am not going to run the whole thing. I am going to explain. Yes, you will be provided the notebook obviously. So what you can do is, basically when you have time, you can run the whole project and then you can understand what is happening. Okay, so what data set are we using? First let us talk about that. So we are using a Flickr 8K data set. So we are using Flickr 8K data set. As the name suggests, it has 8000 images, and Flickr 8K dataset basically has that you have images, JPEG images, and for each JPEG image you have 5 captions. So think about it, right? This whole girl in pink dress can also be written as pink dress girl wearing a pink dress. So there are a lot of ways in which you can caption the same thing, right? So what happens here, for each image, for each JPEG image, for one JPEG image you will have 5 different captions. So this is one, this is second, third, fourth and fifth. So you will have 5 different captions. These all captions mean the same thing, but the language in which it has been arranged changes, it differs. So this is what we are going to do. So for each image you are going to have 5 captions. So now you can understand the data set has increased by a lot. So that is what we are going to now understand, how this has been done. So this is all about the data set. So what we are going to do is, first we are going to download the data set and the text file related to it. So the text file, what the text file will contain, it will contain contain the name of each image, and for each image the captions for that. Okay, so that is what it will contain. So we are going to go for wget. Wget basically downloads everything. So here you can see the download process happens. It has been done. The next thing is basically unzipping your data sets. So now since these data sets have been downloaded, they are in the zipped format, so you need to unzip it. So after unzipping the whole thing, what happens is, see, you can see you have images, different images. So you can see here, right? So here you can see that images have been inflated. Inflated means as in what? They have been unzipped. Now here we have some imports. So what are the some imports? Let us talk about. So see, you have numpy import, then from numpy you are also importing array, then you have matplotlib import, you are writing a magic line of matplotlib inline. So what this will do is basically you can use matplotlib at any time. Then you have importing of string, os, glob. If you remember, if you know, I don't know whether you know about glob or not. So glob is basically a library. So glob is a library, and what glob does is basically it captures or it tries to match different strings of the same format or different file folders of the same format. So if I do glob star.jpg, so in that case what it will do, it will capture all the JPEG files, or if I do star.pdf, it will capture all the PDF files. Okay, so that is what glob does. We'll see how it is relevant in our case. Okay, so after importing glob, we are importing pillow, and from pillow we will be importing image. So this will basically help in predicting the extracted features. Okay, then you have from keras, you will be importing importing input and layers. You will be importing optimizers. There are different optimizers that we will be using. There is pre-processing. We will be importing tokenizer. So if you remember tokenizer and pad sequences, we have talked about this when we were doing sentiment analysis using LSTMs. Okay, so if you remember tokenizer, what it does, for each word what it will do is so each word it will convert it into a particular number. So each word will be assigned a particular number. Now here is one thing that you need to remember. Okay, so if you are using a tokenizer at one time, it will give, let's say it will give cat, let's say it gives number 1, and dog it gives number 2. If you use tokenizer one more time, these values may change. Now this might become 2, this might become 1. So you have to remember, if you are saving the model and rerunning it, you need to also save the tokenizer. Okay, so you can save the tokenizer using a pickle file or something like that. Pickle file is the easiest way to do that. Then you have pad sequences. Pad sequences, what it does is it converts all your sentences into the same size. So what will happen once they are converted into the same size? In that case you can easily run your model, because your RNN sizes or LSTM number of cells that you will be using has to be prefixed beforehand. Then you will be importing layers, LSTM layer, embedding layer, dense layers and everything. And then you will also be importing inception. So for extracting features here that we were talking about, the features that get extracted here, yeah, the CV, the extracted features, for this part we are going to use inception v3 model. So the baseline model that we are using is an inception v3 model. So that is there. Then once that has been done, you are also from inception v3 you are also importing pre-process input. So keras, this is a very fine thing about keras, right? So along with the model and the weights, it also provides us the pre-processing steps itself. So you don't have to pre-process, or you don't have to go and see the dimensions of the actual image to and how much it needs to be changed so that you can fit it into a model. It itself provides pre-process input, which already pre-processes the input based on the model that you are using. Then the rest is two categorical and pickle. Now why these will be used, we'll understand one by one when the time comes. Okay, here we are defining just some path. So my token path is basically flickr 8k token.txt. Token path basically is what? It contains your image and it contains the caption for that image, right? And each caption, by the way, each caption you can see for each image. So this image, you can see the image name is the same. For each image with the same name, it has 5 captions. You can see #0, #1, #2, #3 and #4. See, if you look here, a little girl in a pink dress going into a wooden cabin, a little girl climbing the stairs in the playhouse. See, all these have the same meaning. So that is what I was talking about. So these are some of the paths that we will be importing. Once this path has been imported, here is what you can see. So we will be opening a token path. So token path is what? Your token data set. So once you open the token data set, now you can see here image names are same, and for each image name you have 5 different captions. So you can see here. So what this does is basically, it is very difficult, if you think about it, it is very difficult to get a lot of images, right? So one augmentation method that you can think about in this manner is, there are different ways to write a text. You need to just change a combination of input and output. So you can change the combination by changing just the output and not the input. So your image remains the same, however your caption changes. So now instead of having one caption per image, you have now 5 captions per image. So that increases your data set by 5 times. Okay, so this is a massive increase, and this is a very good technique of augmentation in this case. So that has been done now. So our path has been given. We have downloaded the data set and everything. The next part here is basically, we are going to create a dictionary. So my dictionary name is basically descriptions. So my dictionary name is descriptions. And in descriptions dictionary, what I'm having is keys and values. So for each key, my key contains the name of the image. So it contains the image ID, and the value for this is basically a list. And this list contains all the 5 different captions. Okay, so do you understand what is happening? This is a variable descriptions. The description is a dictionary. It is a dictionary variable. So in dictionaries, what happens? You have keys and values. The key value is basically the image ID, and the value is basically a list, and this list contains all the 5 image captions. So that is what is happening here. So we are splitting the data set and we are creating a list. So if you run this, see, you are first of all going through each and every line in doc. So doc is basically this part here. So we just saw a part of doc. You can see this is basically my document. Okay, so we are going to split each and every line doc line based on \n. So \n means we will be taking one line at a time. So for each line, what we are doing now, we are splitting it in the form of tokens. So tokens, how they work is basically, we will be splitting them. If there is nothing mentioned, in that case split happens because of a space. So I will have, this will be my first token, this will be my second, child will be third, and so on. Okay, so you understand the token concept. So now my line has been split. Now, so that means this becomes my first token, becomes my second token, child becomes my third token, in becomes my fourth token, and this is for line 0. Okay, so if you increase the line number, the value changes. So here you can see tokens have been split. Once that has been done, now what we will do, we will take just the image name. We are not interested in the extension of it. Okay, so we are not interested in the image extension. So my image ID is basically this value here. Since we are not interested in that, since this is one token, right, this is one token, so I am going to again split it on the basis of a full stop. So now that I have splitted it in the form of a full stop, I have 2 parts. This is my first part, the image ID, this is my second part. So I am not interested in the second part, I am just going to take the first part. The first part becomes my image ID. Then you have image description. Image description becomes everything that is from here onwards for each image. So if we look into descriptions right now, you will be able to understand what is happening. See, you can see here, this is my key value. So my key value is the image ID, that is the name of the image after removing the extension. Okay, and then you have your description here, or the value here. The value is what? This is basically a list. So in this list, what it contains? It contains 5 different captions for the particular image. So you can see a dog is shaking off water, a dog shakes his head, a dog shakes off water, a dog shakes off water and gets comforted, the dog is shaking off water off his body, right? So these are 5 different captions. All these captions, if you read, you will be able to understand they are the same thing. So this particular image, it has something of this format, and these are the 5 different captions. So this is basically the key, and this list becomes the value. Take another example here. So this is basically my key, this image name or image ID, and this becomes the value. Okay, so the value is basically a list, and these are the list, these are the different elements in the list, right? So this is basically my descriptions value that I have done here. Why this will be required, where this will be required, we are going to talk about it, but for now let us just understand what description stands for. So this is what descriptions contain. right? The next part that we are going to do is basically, this is a basic pre-processing step or a bit of cleaning step that you can call it. So this helps in basically removing the punctuations, making it lowercase, removing the digits and so on. Okay, so that is what we are going to do here. So you can see here, the first thing that we are doing is we are going to split it, the description. So for key and description list in description items. So if you remember, our description items, it had key and it had value. In the value there was a list. Okay, so we are going to split it, and for each and every value in the list itself, what we are going to do is we are going to convert it into lowercase, and then we are going to remove all the punctuation. Here make trans basically does is basically it creates a table for substitution or removal. So that is what we are going to do here. This is a basic pre-processing or cleaning step. Let me write it here. So this is a basic cleaning step or cleaning writing step that we have done. Now let us look into one of the images for better understanding. So you can see this is the image here. Now these are the 5 different captions for the particular image. A child in a pink dress is climbing up a set of stairs in an entryway. A child going into the wooden building. See, you can see all these captions, they totally match the image, right? No caption is right, no caption is wrong. So this is basically an example of how our data set will look like. I hope that is becoming clearer. So once that has been done, here you have basic cleaning. So what is happening is we are going through each and every key and description list in the description items, and for each and every value in the list itself, that is for each and every sentence in the list itself, what we are going to do is we are going to convert it into lowercase, the whole thing into lowercase, and we are going to remove the punctuations. Okay, so that has been done. Now here what we are going to do is we are going to basically count the vocabulary. So what counting vocabulary means is the number of unique words in the particular data set. So I have 8,828 different words. Okay, so this is basically your counting of vocabulary. Now what we are going to do is we are going to make some new changes. So we had description which contained key and values, right? But that is not enough. We have to make a few more changes. So this is what we are doing. We are going to make another variable in the name of new descriptions. So what will happen in new descriptions basically is it will go through each and every value in descriptions. Okay, so descriptions is basically a dictionary. So it will go through each and every value, and for each value, see, for each image ID, it will have here, it will have one description. Then the next line, it will have the same image ID and another description, but this time. So in the next one, it will have the same image ID. See, the ID remains the same. If you see properly, this ID is similar to this ID. So the ID remains the same, but you can see the caption has changed. So we have basically what we have created kind of a sentence, a sentence, and in this sentence what is happening is it is having the first word as your image ID, the next words are basically the caption, and then that is followed by a \n. Then again the same thing happens. So you have the image ID, captions, \n, and so on. Okay, so this is basically what your new descriptions. Next here what we are doing is basically, see, this here what we are doing is we are creating a set. This set will contain what? It will contain all the IDs for my training. So if you look here, this is all the names of the images for training. Here what has been removed is the extension has been removed, .jpeg has been removed, but the rest is the same. So this is my image name, image ID, and there is no extension to it. Okay, so this is basically your training set. Now what we are going to do is we are going to download Glove. So what is Glove? Let us talk about that first. So we have talked about Word2Vec, right? We have talked how Word2Vec was released, how it works and everything. So like Word2Vec, we also have Glove embeddings. So what are Glove embeddings? Let us talk about that. See, Word2Vec, when we talk about what is Word2Vec, Word2Vec was basically an autoencoder. What it did was basically it reduced the dimensions. That is the main task of it. Okay, so it reduced the dimensions, so you can represent a particular word in some number of dimensions, right? So that is basically the whole point of Word2Vec. So Glove is the same thing. Word2Vec was released by Google, Glove was released by Stanford. So here what we are going to do is, we are going to convert, now that we have the words, see you have the words and you need embedding for it. So instead of making a layer for embedding itself, instead of layer embedding, because in here what will happen, it will happen the same thing, you will have the input here, you will reduce it to a particular dimension and then you will have the output recreated again. Okay, so this is basic embedding of yours, but this is layer embedding, so it will use whatever words are there that is present in your vocabulary itself. Since our vocabulary has only 8,000 words, so it will just use those 8,000 words to create an embedding. But what if instead of using this, we use a much larger embedding, like glove embedding for instance? So in that case what will happen is, these words we will be using an embedding layer, so we will be having words. What will happen, so you will have words, you will have a sentence, a caption, let's say a caption. So this caption will be tokenized. How will it be tokenized? So you have different words, right? So you have a caption is basically a set of words, so each word will be tokenized, so it will be given a number. Then once the tokenization has been done, the next part will be padding, and then this will be followed by embedding. So there are two types of embedding, either you can create an embedding of your own or you can use a pre-trained embedding. So in this case we are going to be using a pre-trained embedding, because I have already showed you how embedding can be used if you are starting from doing everything from the scratch in sentiment analysis using LSTM. So here we will be using a pre-trained embedding. So what embedding will be using, we'll be using glove embedding. So the reason why we are using glove embedding is because it is easier to get than word to vec. First that, and secondly we need to understand how this works. Okay, so here we are going to download the glove embeddings and we are going to unzip it. So when you unzip it, there are 4 different values that you are going to get. Okay, so once after you unzip it, you will have glove.6b.50 dimension, 100 dimension, 200 and 300 dimension. So when we say 6b basically means 6 billion data sets. Okay, or data sets, or we can say 6 billion different words. So it has been trained on 6 billion words, all right, and 6 billion words, and they are of different dimensions. So you can use 50 dimension, 100 dimension, 200 or 300 depending upon your preference. We will be using 200 dimensions here. So I downloaded the data set, I downloaded the glove, the embedding. So what we are going to do is, basically now we will, instead of using an embedding from scratch, we will be using a pre-trained embedding, because it has a larger value, so it understands words in a way better way when you compare it to smaller embeddings. Because think about it, this is 6 billion, this has been trained on 6 billion different data points, or 6 billion different words. This here, our whole vocabulary is only of 8,000 words, so you will not be able to compete with that, and this will cause a lot of overfitting. Hence it is better to always use some pre-trained embeddings. Now here what is happening is, see, here we are just basically creating a list of all the file values. Okay, so for file values, I mean, if you see here, see, now this basically contains all the different images along with the extension this time, right? And then here we have, if you see train image, so there are two things you need to understand. Once when we were using the token txt, right, when we were using this file 8k token.txt, it contains the name of all the files that we will be using, or all the dataset, entire dataset, but we need to split it into train and test, right? So hence here what we are doing is, basically we are going to split it into train and testing. So this is basically, see, the first part is basically this is basically all the images that you can find. Okay, this is the entire dataset, entire Flickr 8k dataset. Here you have the path to all the images for your training. So these are path to all the images for training, and in the same way, if I do test image, so in that case it will have a set of, it will have a list of all the path for testing images. All right, so this is basically the difference. We are now creating two lists. First list contains my path to all the training images, the second one contains the path to all the testing images. Now why we are creating so many variables, I am pretty sure you might be thinking about it. See, there are a few things that are required and that are like compulsory you need to have, and to achieve those variables you need to create some other variables as well. Like you could not have created new descriptions without a descriptions variable, right? So there are a few variables that need to be created for the other variables to work. So that is what is the whole point of this, and that is what we are doing. So once that has been done here, now what this part is doing is, see, I am not going to go through all code each and every line by line. The reason why is this is like a very big project in itself. You can see this is a very big project, so I am going to explain very shortly what is happening. If you have any problems, you will be having this notebook with you, right? This notebook is already present with you, so you can go over it one by one slowly to understand the whole thing. So here what is happening is, see here we are going through it, and we are, for each sentence we are adding a start sequence and an end sequence. So these are the two tokens that we will be adding. So if you remember when we were talking about in here, right, this start and this end, instead of having start and end, we are going to have start sequence and and end sequence. Now as I said, these values, these are just tokens, so you can change it according to your requirement. So if you remember, we added \t and \n when we were doing English to French translations, right? So this can totally depend upon your requirement, your needs, your suitability, or whatever. So that is what we are going to create here. So now let us look into train descriptions. See, now again the whole thing is the same thing, but here the difference is, basically when we were talking about descriptions contained both your testing and training descriptions, right? Now this has been changed to train descriptions. Now in train descriptions, what will happen is it will contain just the descriptions for training. Okay, in here also what is happening is, it has a key and it has value. In the key it is the ID of the image, okay, and in the value it is having a list, and in the list what is happening is it is containing all the captions for that particular image. But this time the captions have been properly cleaned. So how has it been cleaned? So it has been converted into lowercase, number one, and number two, what has happened is it has been removed of, it has been devoid of, stripped of all the punctuations. Okay, so that has been done, and start sequence and end sequence has been added to it. So why this start and end sequence is important, if you remember, we have talked about this as well. So end sequence tells us when to end the whole thing. So as soon as your model predicts an end, you know, okay, this time I have to stop and I cannot pass the values more into the next LSTM, because you don't know when to stop it. Okay, you don't know, only the model understands when to stop. Hence you need to have this end and start sequence. So this is basically the whole thing here. So this is your train descriptions. So the whole point of doing all of this was basically to get your train descriptions here. Now what we are going to do is, basically if you run this, let us look into all train captions. See here what is the change. Instead of having a dictionary this time, now this is basically what will be used for training, right? You have to remove what is used for training. You will have two inputs. The first input will be your image, and that image you will have the ID and everything. You do not require the ID anymore. The reason why is because we will be just passing the text into the LSTM, and the IDs or whatever image is there, that will be passed itself into a CNN. Okay, so this is basically what your training will look like, or what your data will look like when it is passed through an LSTM. So this is basically a list of the entire data set that will be used for training. Now here what we are doing is, basically if you look properly, we are just finding the length of vocabulary. So what we are doing is basically we are using a threshold of 10. So that means if there is any word that occurs more than 10 times, or 10 times or more than 10 times, only in that case will that be added to our vocabulary. So if you remember, our vocabulary was like 8,000 earlier, now it has reduced to 1600, because there are a lot of words that are used only once, only twice, only thrice, and we cannot use those words because they will just add more noise to our data set. Okay, so it will add more noise to our data set because it has only been used once or twice, so that does not help us a lot. Hence we keep a threshold. You can change the threshold from 10 to 5 according to your needs, according to your requirements, but that will just add noise to it. So if you want a robust model, just try to keep it in the same value. Here what we are doing is, instead of using tokenization, what we are doing is we are just creating an index of the whole let me show you. So this basically creates a dictionary, and this dictionary will contain a number for each word and vice versa of that. So if you look here, see, each word now has a particular number assigned to it, right? So this can also be done using tokenizer. Okay, so this can also be done using tokenizer, but there is the other way of doing it. So that is what we did here. We used this value. Okay, so we created word to index. You saw word to index. Let me show you how index to word look like. This is just the reverse. The numbers are the same. If you will look properly, the numbers are the same. 949 for retriever, the same was there here. So what is happening is basically your key and value has changed. So earlier it was retriever number 949, and here it is 949 number key, and the value is retriever. So what happens is, once you are converting the values, right, for training you have to convert it into numbers. To convert into numbers you will need word to index, but once you are getting the output, the predict values, in that case you will have to convert it back. So the numbers have to be converted back into words, hence you will be using ix to word here. So these two are the dictionaries. You will have to save these dictionaries if you want to use them again. Okay, and if you are using a tokenizer, in that case save the tokenizer value as well. Here we are finding the maximum length of description. So here what is happening is basically the maximum caption length is 38. So we have 38 words, and that is the maximum, the longest caption. Okay, so the longest caption is basically a caption with 38 words. So that is what we found out here. So here comes the part where we will be loading the glove models. So you need to understand that even though you have a text file, right, this text file is very huge, by the way, and what it contains is basically, it contains in this format. The text file, if we talk about it, so our text file, it contains a word, and this word has some 200 dimension representation. So this is how, so this is word 1, so you will have the same for word 2. So this is basically what, if you think about it, this is basically a key word dictionary. Okay, so this dictionary has been stored into your txt file. This is so huge that it takes about 7 to 8 seconds to only load the whole thing, right? So if you see here, it takes a lot of time to load. So it says no such file or dictionary. The reason why is because I have not downloaded it. Let me download it. So this takes time to download itself. So we will be going through this. I'll show you how this is working first. So here you can see we are loading the whole thing. Once the value has been loaded, what is happening is it is going through each and every line. So for each and every line it is doing a split. The word is basically value 0. Once you are splitting it, it gives you two values. The first value is basically the word, and the rest is basically an array. So this array basically is your coefficient value. Okay, so here the download is still not over, because you can see here you have the gray number, so that means it is still working. Once this converts to yellow, we can do this part, and you can see how this loads, and this loading takes a time. When I say, I actually mean that it takes time. Here the next part that we will be doing is basically, once that has been done, now we are going to go through all the words that is there in my dictionary, and for each word I am going to be assigning what? I am going to be assigning it a vector. So you can see here I am making an embedding vector. The embedding vector is equal to my vocab size comma embedding dimension. What is my vocab size? See, my vocab size is basically here. 1659. How did I get this vocab size? See, 1659. So if we print the vocab size, okay, it will not be able to run because it is still downloading. I think the server speed there is pretty slow, so it is taking some time to download. It still says 46-45 seconds. So I will show you one by one. You will be able to see vocab size. Vocab size is basically this size here. You can see the length of vocab, which is 1659. Because why is it 1659? Earlier it was 8000. The reason why is most words are used only once, so they will be acting as a noise. So in that case we need to increase the threshold, and we will be only using words that have been used more than 10 times. 10 times or more than 10 times. So that is what vocab size means. So here what we are doing to do is basically for each and so we are creating an embedding value here. So you can see we are creating a numpy 0 value. We are creating an array. This array will be of this size. So this will be here. So my array will be in this format. This will be equal to my vocab size. Vocab size basically each word. So let's say my first word is this. My next word is girl. In this format, so this here, this will contain the 200 dimensions for this girl. Here this will contain 200 dimensions for girl, and so on. Okay, so this is basically how my array will look like, embedding array. And once if it is not present, in that case it will be left as empty, it will be left at 0. So what this means is, suppose in my vocabulary of the Flickr dataset, the 1600 words, there is some word that is not present in the 6 billion library. In that case it will be left empty. Alright, so now let us run this. See, the loading part takes a lot of time because this is a very big library in itself. And also if you will see here, the vocab size is 1660 because we have added a +1 to it. So if I remove this, it becomes 1659. See, the whole thing has been loaded, but it took a lot of time because this is a very huge library. Once that has been done, what you are going to do is basically convert it into the embedding vectors. These vectors, now what they will be doing is, they will be passed for training. Then now what you are going to do is, now you are going to define your basic CNN model, the baseline model that you will be using. So here I am using Inception v3, and the weights I am using is ImageNet, and that model but the difference here will be, instead of using the input will be the same, model.input, the input remains the same, but instead of getting output value, the output is basically the value it will show in softmax, because Inception is basically a classification model, right? It will give you my classification whether this model is in a softmax, whether this is a chair or this is something else or this is some other part of whatever. Okay, so this will be basically used as a classification model. But here, since we don't need classification, if you remember back here in our structure, we don't need classification, we just need to extract the features, right? See, we need to extract the features. So to extract the features, what we are doing is, we will be using all the layers except the last two fully connected layers. So we will not be using those two fully connected layers, and then what this will give us, this will give us all the features that we need. Next we have a pre-process step. In pre-process step, what is happening? The image is getting loaded, image is getting converted into array, because all images need to convert into array for it to be used in a keras model. Okay, then it will be expanding its dimensions because we will be adding one more axis to it. And then finally we have pre-process input. Pre-process input is what? The pre-processing one that is there in here. So if you remember, we talked about this as well. Here, pre-process input. So keras itself, for each model, it provides a pre-processing a function. Okay, so this function basically defines all the pre-processing that you will be needing. So this is what is happening, and this pre-process now finally gives me the output. So here what is happening is, I am going to encode it. So what I am going to do is, basically I am going to make an array. In encoding, what will happen is, I am going to make an array, and the array will be in this format. This will be the first image, okay, and this will be the encoded vector for the first image. This will be my second image, the encoded vector for second image. How am I getting this encoded vector? This encoded vector is received how? First it is passed through a CNN baseline, that is an inception v3 in our case. So it is passed through inception v3. Last two layers have been removed. So in this case, once it has been passed through inception v3, what will be my output? It will be all the features. So this will now basically give me an array. The first value will be the features of the first image, the second row will be the features of the second image, and so on, okay. So this is basically my captioning part here. This is the encoding part that I am doing, and this will basically return me a vector. So here it is given a vector, but it is actually a numpy array, okay. So this numpy array will contain all these values. So this will be happening, and we will be doing this both for training and testing. Now this part requires a lot of time. When I'm saying a lot, I mean a lot of time, okay. So what you can do is, when you are doing this, after you have done this, you should not do it all the time. So in that case, what you can do is, basically you can store the values in your drive in a pickle format. So the next time when you are doing it, you have to you can just load it and it can start working, instead of doing everything from the start or scratch itself, okay. So this is basically the storing part. Now the next part is basically defining our model. We have done this. Our model for CNN has been defined. So the next part is basically defining the LSTM model. So here we will be defining our LSTM model. So you have inputs. Inputs will be of shape 2048 comma, and then you have dropout. So why 2048? Inception v3. If you see inception v3 how it looks like, if you go back to the architecture. So inception v3, if you remove the last two layers are fully connected layers that give me 1000 output, okay. So the output is of 1000 value, 1000 softmax. So if you remove these two, you are getting a 2048 output, right. So that is what my input will be, because that will be my encoded vector and that will be the input size. So it is 2048. This is followed by a dropout, because for every LSTM you need a dropout, okay, and this is followed by one dense layer. So what I am doing it, I am going to be reducing this 4028 into 256 before I'll be feeding it into my embedding and LSTM. Once that has been done, what will happen is, I will now pass it through the embedding layer. Here, instead of embedding, see, embedding I am using, the layer is embedding, it's the same thing here, but I will be using what? Embedding dimension, and mask 0 equal to true. So embedding dimension is basically what I got from the one that I described here. So this was my embedding matrix, and that is the matrix that I will be using, okay. So next is basically, this will be followed by another dropout. For every LSTM it is good to have dropouts. The reason why is because it can lead to overfitting or gradient explosion or vanishing gradient problems. This will be followed by LSTM. The number of output features I want is 256. Now once that has been received, the next thing what we will be doing is, basically it will give me two values. Now these two values will be added, okay, and once these two values, what two values are being added, by the way? The value here that you got from dense layer, that is from the CNN, and the value that you got from LSTM. Once these two values have been added, it will be passing through another dense layer, so it will be able to understand both CNN and NLP features, and then finally it will be passing through a softmax layer. This softmax layer will have what? How many values it will have? It will be equal to the vocab size. My vocab size is what? 1659. So we will be using 1659 different words, and it will be able to predict which word the next the next word should belong to which category, okay. So that is what one thing, and then finally we will be defining our input, the model. So it has 1 million, 1.8 million trainable parameters. You can see it is a lot. These two are basically the saving features. Like I said, you can save the features. Here here I gave an embedding value, right? I gave everything, but here you can see I am setting weights for it. These weights are my embedding matrix weight. Embedding matrix was where? Here. So here you described your embedding matrix, right? So these are the weights that you got from Stanford glove model, and that is what we are going to set the weight as, and then that layer will be trainable as false. So we will not be training the embedding layer. All the other layers, yes, they will be trained as they were being trained. Then the next is model.compile. In model.compile, what is happening? You have the loss, categorical loss, and optimizer is Adam. So that is done, your model has been compiled. But here is the thing, my data set is pretty huge. If you think about the data set size, it is very large. It is what, 8,000 different images. So, and for each image you have 5 different captions. So it has 8,000 into 5 is the data points, number of data points that we are dealing with. That is large. So you need to divide it into batches. But here is the thing, what is the input for your data? If you think about it, what is the input? In one model, your input is a CV, computer vision and image. In the other part, the input is what? The input is your text. So you have 2 different inputs. So you cannot use the basic batch size and pass it one by one. Okay, so you have to create what is known as a generator. So a generator, what it does is for custom data points, or for data points which cannot be passed in the form of batches, you have to create a data generator on its own so that it can be passed. So this is what the data generator does. So how will this work? Let us talk about this. Okay, so this is my data generator that I have defined. Here what we are doing is, for each key and list in the description items, I am going to what? I am going to extract the photo. Once the photo has been extracted, what I am going to do is, I am going to extract the feature vector from here, and then I am going to convert it into, here what is happening is, word to index is basically I am converting each and every word from the description list, from all the different captions in the description list. I am converting each and every word into tokens, right? And once that has been done, I am going to split it into in sequence and out sequence. In sequence and out sequence, what does that mean? This is very similar to your decoder input data and decoder target data. So what does that mean? So in sequence is basically all that will be passing in. Okay, so all the input that will be passing in. So let's say start girl in pink dress, end, right? This is your in sequence. Your out sequence will be girl in pink dress, end. This is your out sequence, right? So this will be what? This will be one time step ahead. If you remember, we have talked about this. So this is what is happening here. We are describing it in sequence and out sequence, and then we are going to pad it. We will be padding it what? We will be padding it to the maximum length. If you remember, the maximum length is 38. How did we get 38? Again, if you remember, let's go back. 38, how did we get? This is basically the maximum number of words in one sentence, so that no sentence is left behind. All the words are of, all the sentences are of particular size. So padding has been done. This part has been done, and then finally my out sequence, it will be converted into categorical value. So what will happen is, basically it will be a categorical value. So if you remember, when we were talking about LSTMs, I told you multiple times, when you are going in, right, you get hidden values, hidden state, and if this hidden state is passed through a softmax, it gives you my y values, my output values. So this is what is happening. My out sequence is being converted to categorical. So what will happen once it has been converted to categorical? It will be now used for my output to give me the y label values. Okay, so now this to categorical, how much size will it be? It will be of 1659, because we will be using 1659 words. So whatever word you will see in the caption, it will be from among this 1659 words. It cannot predict any other word. So here you can see x1.append y1, and I am getting this whole thing. And as soon as I get this, I have created photos per batch. Photos per batch is basically a number. So this is basically equivalent to your batch size. Okay, so this batch size, as soon as it reaches this batch size length, what will happen? It will give me these values. Okay, so it will give me, it will pause the whole loop. Once the loop has been paused, it will get out of the whole function, and it will give me array x, x1, array x2, and array y. What is array x1, x2, and y? So array x1 is the photo. Array x2 is what? It will go as your input. So this was, if you remember in LSTM's sentiment analysis, this is equal to your encoder input data, decoder input data, and decoder target data. So this is what the whole thing is. So this will give me an array of that, and it will change all the values and start from 0. So as soon as the number is reached, as soon as 3 is reached, it will give me the output. It will complete one epoch, and then it will go back again and start from here. this is the next line it will start from. So here it will go back again it will go through the whole process, then again next 3 is reached, it will pause, it will give me the values, and then so that is how basically the data generator is working. Okay, now here what is happening is I analyzed the generator, I have given it a name and everything, and then you can just pass it in model.fit and you get the values. So you can see here I have trained this. Just takes a lot of time, so you can train it on your own. So it takes 278 seconds if I am using a GPU, so you can understand it takes a lot of time. Then you can save your model, and you can also save the weights if you want to. That totally depends on you. The next thing that we are going to talk about is greedy search and beam search. Now these are two very interesting topics you need to understand. Okay, so when I talk about greedy search and beam search, right, these are two different types of search algorithms. What does that mean? Let's say I am predicting a value. Okay, so I am predicting a sentence. So that sentence is girl in a pink dress. So my model will first predict girl, right? So girl will be predicted. How will girl be predicted? It will give me a softmax. There will be a softmax 1659 values. Girl will have the highest value 0.8. So it will predict girl. The next, the girl will pass here next for the next LSTM. It will pass as input, and then it will pass. Then again it will pass through another softmax. Here the softmax will have in as the highest probability. So this will predict the next word as in. In that format you will have the whole sentence. This is basically the premise of greedy search. So what is beam search? So greedy search, what as the name suggests, it searches everything greedily. So what does that mean? It will search everything in a greedy format. So whichever has the highest value, it will go and give that format. Beam search does not do it in that way. What beam search does is, let's say here you have girl in a pink dress, so it gives girl as the highest value, right? And then it will give, let's say, another one, so it gives little as the next highest value. So what it will do is basically it will use girl and little. It will use, if my beam search value is 2, let's say my beam search value is 2, in that case what will happen? It will use girl and it will predict the entire sentence using girl. Then it will go through little and it will predict the entire sentence using little. Sometimes what happens is it might give the highest value for a particular word, but that might not be the probability, or that might not fit in very well when you compare it with the whole sentence. Okay, so it might give you a very high value for girl and low value for little at the moment, but if you increase the chances, if you search for both values, it might happen that you get a sentence from little which gives you a higher probability or a higher chance of happening than one with a girl. So here it is searching greedily. It is very fast when you go for greedy search. Beam search is slow, but it gives more accurate results. So it will give little. So next what will happen after girl? The whole thing has been passed through another LSTM, and this will be followed by a softmax. Now this softmax will again give me values 1659. Again we will be taking top two values and then we will be forming the next words with it. Okay, so this goes on like this. So you have girl predicted, you have little predicted. Okay, so once this has been predicted, now from girl itself you will predict two different next two highest probabilities. Okay, so girl in, girl with. So from in, again you will be predicting next two words from the next two words. In that case, what you are going to do is basically you are going to form a tree, and in the tree finally you will have all the values. Let's say this has been reached, my end has been reached. How do we know that end has been reached? It will give me what? It will give me end sequence as a token. As soon as end sequence has been received, I know the sentence is complete. So once this has been done, what we are going to do is for each of the sentence that can be formed. Okay, so this sentence here, this sentence here, this sentence here, all these sentences that can be formed, what we are going to do is basically we are going to use that and we are going to multiply all the probabilities. Okay, so the one which has the highest probability will be the sentence, okay, which will be the most accurate sentence. So that is what beam search does. So here is an entire code for this. What I can say is basically you can go through it, you can understand it. It is not that hard, but I am not going to go and discuss it. I have discussed the entire process as it is. So you can go there. Here what we have done is basically this is the final prediction. We have taken one image, we have encoded the image, encoded as in like we have converted it into as will be required for the inception, and then we have read the image, and then we have gone through greedy search and beam search. And you can see in greedy search what it gave me the output: a dog is running through the snow. Not wrong, it's all right. when you are using beam search as k equal to 3, a white dog runs through the snow. Okay, not exactly. A brown and white dog is playing in the snow. Kind of working. A brown and white dog playing in the snow, brown and white dog playing in the snow. So you can see when you increase the beam search, the value becomes a bit better. You can see it is giving now at least that there are 2 dogs instead of 1 dog, right? So you can see beam search is way more accurate. So you will be given this notebook, don't worry, you can run everything on your own. You will be able to identify. This is a very interesting project as it is. So what I would say is go through this one by one, run the whole thing. If you have any doubts, do text me. I will be sharing, this is here, this is my LinkedIn ID. So do text me if you have any problems, any doubts, any queries in that way. And this is it. I hope you enjoyed the video. I hope you enjoyed the project. Do add it in your resume. Do share with me whatever recommendations you have, whatever changes I can make. Do share if you enjoyed the project and all your journeys and everything. I'll be looking forward to it. And that is it. I hope you enjoyed the video and keep learning.